For the rest of this module, we'll talk about ions and ionic compounds. We'll start with the properties of monoatomic ions and see how they parallel those of atoms. Then we'll deal with the names and formulas of monoatomic ions and the compounds that can be made from them. We'll repeat this then with polyatomic ions. So, what about monoatomic ions and their properties? There are a number of themes in monoatomic ions, including their charge, electron configuration, radius, and names. These should look familiar because we dealt with these issues when we talked about atoms. Here we want to highlight the differences. First, the charge. Of course, the atoms of each element are neutral, but we know metal atoms can lose electrons producing positively charged cations, and nonmetals can gain electrons producing negatively charged anions. For many monoatomic ions, the charge can be determined by the location of the element on the periodic table. For example, the alkali metals in group 1 all form 1+ charged ions. The alkaline earth elements in group 2 form 2+ charged ions. Note that this corresponds to the loss of the valence electrons in each element. Silver and aluminum make 1+ and 3+ charged ions respectively. The rest of the D block metals, along with the F block metals and the metals in the P block, all make more than one ion that have different charges. They are highlighted in the blue box and are called variable in the picture. Along the right, the noble gases, highlighted in green, have filled valence levels and do not form ions. The other nonmetals that form ions are highlighted in purple. The group 17 elements, the halogens, form 1- charged ions. The group 16 elements make 2- charged ions, while the group 15 elements make 3- charged ions. In each case, the charge corresponds to the number of additional electrons it takes to fill up the valence level. Note that the purple boxes do not go all the way to the bottom of the P block, since only nonmetals make negatively charged anions. You may wonder why carbon isn't listed as 4-. That's because carbon is not observed to form ions. Many of the ions in the previous page were formed by removing valence electrons, or adding electrons to the valence level, such that a noble gas configuration was achieved. If we want to write configurations for ions, it's often helpful to start with a configuration of the atom and then add or remove electrons to generate the charge. For example, fluorine has the configuration 1s2, 2s2, 2p5. For the fluoride 1- anion, one electron needs to be added and it will go into the open spot in the 2p sublevel. So the ion configuration is 1s2, 2s2, 2p6, which is the same as neon. Sodium has the electron configuration neon 3s1. For the sodium 1+ cation, the 3s electron is removed, leaving the neon configuration. Where we need to be careful is with the transition metals in the D block. When we talked about orbital energies of the atoms, we said that, for example in the 4th period transition metals, that the 4s electrons were found to be at higher energy than the 3d electrons. This was due to the size of the two types of orbitals. The bottom line is that the 4s electrons are at higher energy, so they will be the first to come out upon forming a cation. The general rule of thumb is that electrons are removed from the highest n orbitals first. Thus, 4s is removed before 3d. As an example, let's take manganese. The atom has the configuration argon 4s2 3d5. In generating the 2+ cation, the 4s electrons are removed, leaving argon 3d5. If we were then to remove an additional electron to make the 3+ ion, a 3d electron would come out, leaving argon 3d4. In many ways, trends in ionic radii mimic trends in atomic radii. In this figure, taken from another textbook, The blue spheres on the left show the sizes of the main group cations. Like the atoms, the ions get larger as you go down, but get smaller as you go left to right. The same general trends exist in the anions as well, although you can find a couple of exceptions. The difference between the neutral atoms and these charged ions is that the trends do not go all the way across. But there is a trend with cations and anions that we can explain based on effective nuclear charge. Let's look at the series sulfide, chloride, potassium, calcium. All of these have the electron configuration of argon, with 18 electrons. Since they all have the same number of electrons, this is called an isoelectronic series. As you go through the series from sulfide to calcium, the number of protons in the nucleus increases from 16 to 20. As we have predicted before, as the 18 electrons feel increasingly more positive charge, they will be more strongly attracted to the nucleus, and the observed radius will get smaller through the series. In order to name compounds, we need to know the names of the individual ions. There are some cations with only one possible charge. These include the group 1 and group 2 ions, as well as silver and aluminum. For these, the name of the ion is the same as the element. So we have the sodium ion and the calcium ion. For cations with variable charges, we use the name of the element and add the charge as a Roman numeral in parentheses. So we make the distinction between the two manganese ions. The one with the 2+ charge is the manganese 2 ion, while the one with the 3+ charge is the manganese 3 ion. For the anions, we use the root of the element name, but the ion name will end in "ide." So fluorine makes the fluoride ion, and nitrogen makes the nitride ion.